Okay.
If you can prove that a force like van der Waals frequencies exists, which is proven, this force does exist. You have covalent bonds, you have ionic bonds, and you have van der Waals bonds. So each of these other modes of being, they have like particle states and stuff. So like if you can, like if the theory is universal, and that like if there is a grand unified theory, they should be able to like they should work the same in the same formal system. So if you have the particle wave duality within ionic pairs and covalent pairs, just to a different extent, like the covalent pairs are almost exclusively biased to the matter arrangement, and ionic bonds are kind of in flux in between. They're kind of part energy, or their energy, they're part matter, part information. They're kind of that in between ground. Like with galvanization and van der Waals forces, if it's part of the same formal system, you have to have an analogous wave particle duality within the van der Waals force. So there has to be a van der Waals particle, even if it's a quasi-particle, because that's what quasi-particles are. They're isomorphisms that have a bias towards information instead of matter, but they're still conversionally the same, made out of the same energy. Their polarity is different. It's kind of similar to like the polarization like in spins with matter and antimatter. There's also it's like a Cartesian plane. You have matter. You have Okay, so this is the positive side on a Cartesian plane. This is the negative side. You have matter and antimatter, and you also have real and imaginary. Or yeah, it could be flipped, but like you have another axis on which to classify types of particles. And in general, covalent bond particles have the antimatter-matter duality, but they're still material more or less. With virtual particles, or quasi-particles is a better definition. They don't have so much, they are more coherent in the sense of like quantum coherence. That means like their potentiality is always expressed. It's like the pre-observed state of quantum states. Like the quasi-particles behave as if they are not being observed, even when they're being observed. That might be a way to explain it. So like they're virtual instead of real. It's a way to express the math of like real and imaginary numbers. Like you have to have
Sorry.
the graph duality between matter and information. You have to be able to convert the one into the other. So if you are able to do that, the other one should exist too. But you have to use graph. You have to use graph duality to superposition, kind of a superposition kind of thing. So it's like when you're doing geometry, and as long as you modify the Cartesian plane to have an axis for imaginary numbers, you can do that kind of math. And that's how quasi-particle math should work. It should work exactly the same way. It's that you have the same numerical expressions, but one of the coefficients is imaginary. See, this ties in with Hawking's theory that time is imaginary. Well, time is sort of like a quasi-particle. It only exists emergently. Like it's the combination of different interactions that cause this type of particle to exist. It doesn't exist in and of itself. That's why it's virtual or imaginary. But once you have this kind of interaction between different types of forces, this particle pops into existence. It decoheres momentarily, but like it's very unstable. like the state that this kind of particle is in is very unstable because it has a tendency to have strange particles, and strange particles don't work very well in a type of coherent universe where there's a bias towards matter instead of antimatter. So like strange particles are kind of like compromises between like the matter bias in this particular decohered universe and like the quantum potential. It's kind of like a halfway point where it's kind of similar to the wave particle duality. It's like that's the wave particle duality is more like the x-axis of the Cartesian plane, and the real imaginary is more like the the vertical axis. So you have the matter-antimatter duality, and you have the real imaginary duality. So that's how quasi-particles work. And so if they have an analogy of like the wave particle duality, they should have, just like other forces, they should have a radiation. So if you have to have a way to express it when it's in the wave part of the duality and not the particle part of the duality. So it has to radiate. So there has to be like a wave that has frequency and amplitude. Frequency, amplitude. Like it's like a squishification process, like a stretching and squishification, and it goes like the way, like how wave theory works in like the way I understand it is like whether it's expressed as a wave or a particle depends on the squishification stretching process. The higher the frequency or the amplitude, like higher the frequency, higher the amplitude, the more the radiation behaves like a wave. When it's more squished, when the squishification process is applied to it, it behaves more like a particle. But it's in between because it functions both as a wave and a particle. So like if you have galvanized things, they emit van der Waals radiation. So theoretically, and because if a van der Waals force exists, there has to be that wave particle duality. So you have to have a force carrier if there's a force, unless it's an emergent force, like what I was saying earlier. Like it's an emergent property, so it's not that there's actually a force particle, like in the classic, in like the Newtonian sense of, like Newtonian and pre Copenhagen interpretation of the wave particle thing. Like in general, you were either a strict wavist or you're a strict particleist, and quantum mechanics kind of brought the two together in like a dialectical fashion. It's like, oh, it's both at the same time, and that kind of a dialectical thinking led to technological advances because of the way binary works. So you can have like you have the possibility to have a quantum computer where you have like the polarity states of like the one or the zero. You can have it superimposed in that it can mean both at the same time because it's using the property of quantum mechanics with that ambiguous duality where it kind of exists in a quasi state between the two or between the two. So you use the ambiguity to manipulate both information like encoding and stuff and with matter. So it should be able to work both ways, theoretically.